So Jean-Pierre Blanchet is a friend of mine who we have given the course on environmental, the modeling of environmental systems for years and years together. And Jean-Pierre is professor at the Department of Earth and Atmospheric Sciences here at UQAM. He's a member of ESCER Climate Center. He has been responsible for developing clouds and radiation processes schemes for 2 generations of the Canadian Global Climate Model. He is a contributing author in the first IPCC. His research is on the intricate feedback processes involving aerosols, clouds, radiation, and precipitation in the Arctic climate system. Since over 2 decades, his work focuses on instrumental development and applications to the observation of cold regions. He has contributed on several major satellite missions, including EarthCare and CloudSat Calypso, parts of NASA's Earth Observing System. He is the principal investigator of the Far IR spectroradiometer for a major climate mission in preparation at NASA for the next 2 decades. On the other hand, his colleague Patrick Grenier is a researcher scientist at URANOS, a consortium on regional climatology and adaptation to climate change, and a adjunct professor at ESCER Center in UQAM, with a background in physics and in environmental sciences. During the last 10 years, he developed climate scenarios for projects in collaboration with researchers in diverse sectors impacted by climate change, including agriculture, tourism, insurance, wind energy, and infrastructures. He also led research activities for improving climate scenario methods and recently gained interest in including conceptual tools from philosophy in his work. He is contributing author for the upcoming 6th assessment report of the Intergovernmental Panel on Climate Change. So each of them will talk for 30 minutes. Then we'll have a 15-minute period of questions and comments. And meanwhile, you can use the chat to formulate your questions. And during the question period, your comments and questions on the chat will be taken into consideration. So Jean-Pierre, go ahead, please. Don't forget to put your microphone, your microphone on.
Yeah, okay, I always forget. Do you see my screen?
Yes, no, we don't.
Non, faut que tu le partages, Jean-Pierre. Faut que tu
d'accord. Oui.
Faut que tu passes un share screen sur
clic de plus.
Zoom. Now we can see it.
Okay,
so go ahead.
Thank you, Serge. And I appreciate this time to talk to you about the aspect of climate that is around processes. This follows up especially from Dr. ALBEDO's early today, and also from Serge's presentation on processes using a diagram of accumulator or stock and flow. So I'll try to make the connection. And my approach is more on the theoretical side to make the understanding of what is behind climate modeling and Earth observation system. And Patrick will go down to the Earth and explain how this applies to a practical society needs. Okay, so I'd like to touch base on the concept of climate processes. This is the key of climate system. And look at the feedbacks. These are really controlling the issue of climate system and what kind of computer needs we need for that. And then the second branch is the observing Earth atmosphere system. And we look at the measurements from ground, from aircraft, from campaign and satellites and also how these measurements can constrain and serve as, big word, validation or verification of models. And how can we reduce the uncertainties by combining observation and modeling? So we know that that climate is warming. There's evidence of that, and there's no uncertainty about the fact that the human is implied into this warming. So that's a fact. This trend were known for many years, many decades. We expected that the pole would warm, and this picture is the observation from a 30-year period or 10-year period over a 30-year baseline, which is a climate period. And this is conform with what the models has predicted before. We also have we know that the temperature trend has been increasing quite a bit, very significantly over the last decades. And now with the models, we can split the contribution. So if we don't have the CO2 or the human anthropogenic effect, we can look at what would have been the natural, that is the green line, and the anthropogenic would be the red line, and the actual is the jagged line, black line. So we can decompose. So this is already a useful assessment to see how our action on the globe is progressing. If we look on a longer period of time, it becomes even more obvious that we've been warming the climate. And this warming has been predicted in 1896 by Arrhenius. It's 125 years ago. It's based on theoretical knowledge, and I insist on theoretical knowledge, not model. Theoretical knowledge, which is some kind of model, but it's an abstract, it's a knowledge of the CO2 greenhouse effect. So we knew about that, and this materialized now. The other aspect of it is what we call the variability. It's not so much that the Earth increased by a degree or two that on the average that has effect. It's the shift of this curve, which implies that the variability here in blue increases quite a bit. Say we increase the temperature by about 1.6 degrees C, then it means that the likelihood that we have extreme event in temperature above 17 average is 32% increase. That's in absolute terms, from 1.3% to 33%. Now, of course, we don't know the shape of that curve. This is just assuming that it's a Bell standard shape, but it can be skewed. But this is the principle. The message here is that the variability is far more important to consider than the average. It's the fact that we're going to get extreme event more often. Now, if we draw a picture of climate is the interaction between many systems, ocean, cloud, forest, vegetation, iceberg, and topography, and so on and so forth. They're all interacting one another to make the picture we know. So in doing a system modeling, we try to represent these subsystems together one by one. So in other words, there's a specialist in cloud, like myself. There's a specialist in forest, like Shang-Wei Peng, for instance, in our group. There's specialists on earth processes, on glacier, on oceanographers, every aspect in chemistry and in human health, any aspect that touch on the global environment. There is people, and these people are having understanding of their science, but they don't know everybody's science. They only know their science. So the system modeling is really a regroupment of people that try to share their knowledge in their field and ask what is implied in the connection between our knowledge in different fields. So system modeling is a tool to address the interdisciplinary questions. Of course, we need to do observations to verify if our understanding is correct. This is the typical science progress, doing theorization and observations. And that leads to an answer. The alternative is to go to some AI expert system onto which we put lots of data, big data, and we crunch to get an answer. This does not explain anything. It just gives us an answer. Scientists don't need that. Scientists need to understand. So understanding and knowledge is the really, really important aspect of our work, and model serve that purpose. While the efficiency and action, once we have understood, can be mimicked by AI or expert system approach. So two are complementary, but not interchangeable. So science is really about understanding, finding, getting deeper into the knowledge, while the society what needs is efficiency and action and decision. So the two goes together. In what follows, I'm going to treat mostly the science part. So science is building on observation and theorization, as I mentioned. Now, models play a role in building of theoretical understanding. A theory is a model of the reality, is what we have gathered from our observations. So we should, I want to mention and stress that it's very important. Models are not barely computer code. That's a misunderstanding, a misconcept. It is, but it's mostly a knowledge of people around a table or in a group, like a group of scientists sharing their understanding on complex questions like climate, human health on a global scale, and ecology, for instance, and other problems similar. So just to follow what Dennis Meadow shows this morning, we can represent a system by a bath or a reservoir, some stock onto which we have a substance like water, energy or matter, temperature, wind, chemical, and any conservative. And here's the word conservative. I noticed this morning people ask what conservative means. It means that the substance can be accounted for. It does not appear by magic. Like the value of an artwork is not a conservative variable because it depends on the subjective evaluation of the person. While energy and matter and water can be only added or subtracted without disappearing by magic. So it's called conservative. It means that the substance can be make a budget, a precise budget, like your bank account. You know, the input and the output, it must be conserved. You don't have things that disappear out of the blue, which would not be non-conservative. So we have some kind of a stock, a tank or an accumulator that is supported by inflow and outflow. So we want to make budget. So there's a variable V, which would be a stock, a conservative variable. And we want to know how it varies. And the variation is the dynamic. The dynamic of a variable, we also call a predictive variable. It's something we can use to predict the future, is expressed by a derivative, a change with time. dV dt is the change of time with time of the variable V. So it's equal to the source minus the sinks of that stock, essentially. So all we do in climate modeling is adding source and sink. And those are actually processes. The feedbacks are when the stocks interfere with the inflow or the outflow of the same reservoir or another reservoir. It means that there is a signal that returns to the input or to the output, just like the feedback in the microphone in a room when it makes noise, because the sound returns from the speaker and return into the microphone. We call it the feedback. Now this is the same thing here. The variable V return into the inflow and make an amplification or reduction if it's negative or positive feedback. So this is the state of the system, is just the value that takes those V variable. You know, if you look at all the V variable and you take their value, and like 10 degrees C and 50 kilometers an hour and so on, it's the state of the atmosphere at that point, at that time. The processes are what creates it. It's the source and sink of that variable. So change of state is essentially the sum of stocks from processes. An example is the simple model by LORENTZ. Just as an example here, I won't go into the detail. There's three equations. X1, X2, X3 are variables. There may be temperature, there may be vertical motion and pressure, for instance. They're defined by the modeler. And that can be modeled as stocks that are interconnected with input and output. And as a result, if we take some values of the parameter, R, B, and sigma here, they're set parameters, then we get an answer. And what LORENTZ found is that this beautiful, simple system mimic or show that the atmosphere behaves like a chaotic system. It doesn't mean that it's not predictable. It's it's deterministic, but it's unpredictable on the long run. It's predictable on the short run. Actually, if we make a little error, this error will grow exponentially with time. It's not wrong, it's just that this is the nonlinearity response of a system. But the important point to notice here is that those lines are not everywhere in 3D. They're a long line and they're confined to attractors. It means that the climate cannot have any random value. Snow over the Sahara will melt. It will get back to the normal climate. So it is confined. And the studying of these change of these attractors is how does the states will evolve in time in climate. So we study the variation of this kind of shape to understand the climate characteristics. Now let's bring it to 4 variables. V is for the wind, they're stock and predictive. Wind, temperature, humidity or moisture, and constituent like pollutants, aerosol, cloud, matter in the atmosphere. So there's also boundary conditions, like outside, if we think of it an aquarium, outside of the aquarium is the room temperature or the light you put in that you control. The boundary conditions are outside. The topography, the sun, they don't change. The background concentration, the soil might be fixed, the vegetation might be fixed, might be not fixed, and the pollutants from multiple sources might be fixed or not fixed. If it's fixed, then it's a parameter. Later, we can free them, add them as new reservoir, new stocks, and increase the model complexity. But let's assume we only have those 4. And these 4 are the basic one. Actually, V, T, and Q are the basic one for the forecast model that you have every day. That's the baseline. Now, these will interact with the input stock by increasing. It's like a birth rate, for instance, for a population. They will affect the wind, temperature, and moisture. There's interaction. Now we can build this interaction. We know that temperature will affect the moisture because we transport moisture from the south and it evaporates or condenses. And we also, temperature will change the wind. And temperature will also change sink of humidity. Now we can do that for all kind of connection. And the modeler try to do that in a very smart way, trying to do it correctly. And try to see what are the links between humidity and pollution? What are the links between? So we ask the guy who's specialist in aerosol and the guy who's specialist in water, talk to him and say, now, how does it affect your reservoir, your area? And each other, we talk to each other and find out how we can best represent. That's the model, how we can best represent these interactions. So we can make as many models as there is people, but that's the building of our understanding. And it's a win-win situation because if we miss something, we see it and we correct it. If we get something right, then we progress. So it's always a win-win situation. There's no loss in here. So we make all these connections. And after a while, then we start, there are many more. We can do feedback. We can say, well, these wind affect the moisture, and the moisture will affect the aerosol or the pollution, and the pollution will affect the temperature, and the temperature will affect the wind back. So we have a closed loop, and a closed loop is a feedback. Now notice that some are positive feedback. Some will increase with a plus, increase the wind, and increase the temperature, and increase the pollution. It might decrease the temperature later on, and that will increase or decrease the wind. So this because there's one negative, the whole loop is a negative feedback. If we have only positive, it's a positive feedback. If we have 2 negative or an even number of negative times negative is positive. So 2 negative is reversing twice, become positive. So every time we have an odd number of negative sign in a loop, it's a negative feedback. Anytime we have an even number of negative or all positive, this is a positive feedback. So you can see we already cannot try to understand how these interact to each other in some way. So these are the states, these are the processes. So it's clear. Now, if I put it more formally in terms of equations, you have the wind equation here. It's called the momentum equation. That's dynamic. It's simply a reservoir of wind. And each of those terms are processes. Like here for temperature, there's radiation. You know that sun will heat the surface. Sun will heat the atmosphere and so on. The condensation will also change the temperature. D is for the diffusion. the subgrid diffusion. Now we can do that for humidity as well, and also for constituents like pollutants, aerosols, and there's for each of those like S emission, S nucleation, condensation, coagulation, chemistry, sedimentation, activation, evaporation, and mixing. These are all processes that must be accounted by subroutine. Now, and here you have the surface reaction. The surface boundary is just the energy balance of the surface. Now, the interesting thing is that a whole climate model can hold in one page. This is a climate model. This is the recipe for a climate model. Now we all have to figure out what's in this C value. What is Q radiation? How does it work? So we have to have the specialist of radiation that does that, and the specialist of coagulation in aerosol does his part. So we put all those knowledge into the system to understand the answer of the whole interaction. Now we go even further. We have several versions of the same process. Let's say we have different chemistry. Then chemistry A and chemistry B can be used. We switch a switch between one and the other, and within just a short change, we can redo the calculation with a different concept of chemistry. And that helps us to understand what is the implication of our inferred knowledge. So it's a learning process. It's a very active learning process. So models are really learning tools. They're not forecasts. They're not meant to say to predict what will be the future. Actually, we can see that this is a wrong way. So these relations are local. They mean they're at points in space and time. Here, now, at that place. And everywhere there's a value. So you can imagine the globe made of little boxes or points in the column, ocean and atmosphere. And each point is a local value that has these equations. So we have as many set of equations as there is point in the model. So the connection between those points and those boxes are made by transport, like a car on the street that will transport people from one place to another. We call it advection is the transport of heat from the south when we have south air from the US that warms one day and cold air from the north that cools us the next day. That's advection. We have convection is the vertical motion of air, and then diffusion because it's mixing, there's turbulence. And also we have turbulence explicitly, and radiation is also a transport process that bring energy from one place to another. Now, if we imagine a whole globe made of those little boxes, grids, and we take a very modest one, 150 latitude by 150 longitude by 50 level. They're much bigger now, maybe thousands by thousands. Now we can make grid of the system. Now if we have, this is 1 million grid point. It's 1 million sets of equations that I showed you on the previous page. And to solve every 10 minutes of the simulation for maybe decades, 100 years. So it's million of time steps. Each with million of grid point. Each point has hundreds of equations because we add more equations than what I showed you actually. So we have quadrillion of equations to solve in real time, to faster than real time to get the answer. So climate simulation can take months and years to calculate depending on the complexity. If you run for 100 years or for 1,000 years, depends on the need and resource. So you can see already why we need, and each point has a surface with the vegetation, roots, leaves, lakes, ocean, sea salt, bugs, and chemistry in the aerosol, in the clouds, and precipitation, and orography, and pollution emission, and so on and so forth, the sun. Each of those processes must be taken one by a specialist that talk to each other and import their knowledge of these processes in the big picture to try to understand what it implies. So when we get an answer for a model, we have to meet again and discuss what does it mean from our perspective. So each specialist explain if it's right or wrong, and what we have, and how can we figure out the result that is very a complex mixture of all these processes. So it's again learning process. An example is the land surface with leaves and roots, and we have in the model several depth of the soil and water in the soil Now, I can go on to, and leaf are capturing droplets of water, and this, each grid point has a fraction of canopy, a fraction of bare soil, a fraction of snow. And there is a mixture of component, the coniferous, leaf, agriculture, herbs, and desert, whatever. So just to take one of these equations, it's a simple one. It's just the moisture, it's evaporation and condensation. Evaporation minus condensation give you a budget. It's like the bath that has water getting in, water going to the sink, and diffusion. So you can see that in the atmosphere. Condensation makes cloud, and precipitation makes a virga that evaporate into the atmosphere. So I will skip those. We can do that for any processes like that. This is for thermodynamics, where you have a vertical motion that cools the atmosphere, produces clouds. You have also condensation that release latent heat. You have radiation that is also another part important for warming. Solar radiation reflected by the atmosphere, solar radiation absorbed by the atmosphere, solar radiation heating the ground, solar radiation reflected from the surface, infrared radiation from the surface to the air, infrared radiation escaping to space. All these terms need to be calculated at every level, every point in the model. But it's just doing budget, really. It's just adding terms. An example, at the surface, you have snow and soil here. It receives solar radiation. And most of it is reflected. This is called the albedo. And some is absorbed, which make it melt and warm up. And they'll be received by the bare ground and reflected, which is less, warm more. So you have a big difference in heat balance between the snow and the bare ground. These also are affected by sensible heat flux, the heat that is produced on the surface, and evaporation, which also transfer heat. So these are the processes we take account of. And now to talk about feedbacks, we have, for instance, in the Arctic, the temperature in the summertime is near freezing at the surface because it's melting. It's like ice over water. It's near the freezing point. Then if we have short wave, it tends to melt ice and before warming the water. So there is a cooling by long wave radiation. Now, if we compare that to the winter time, and you see where I'm showing this picture. In the winter time, you don't get the sun. So you get only the cooling, the surface. So you get an inversion, very steep inversion that might be 40 or 50 degrees colder than the air at 1 kilometer altitude. So you can see that now the cooling is occurring over a cold surface. And if you heat now the surface a little bit by global warming, this has very much efficiency because you don't have to heat the whole atmosphere. You only heat the bottom of the atmosphere. So the heating is strong. You can see in the polar region because of this inversion, because the heating is trapped into the lower level. It's a feedback. It's one of the many, many feedbacks. So another example of feedbacks is the surface temperature that affect the ice extent. It reduces, it's a minus sign, which affect the albedo, which is a plus sign. When you melt the ice, you decrease the albedo, so it warms further. It reflects shortwave radiation. It changes the outgoing long wave radiation, the cooling, which affects the temperature. So you get another feedback. Now you can do that for the snow as well, which would feedback negative and positive, it compounds. Now the ice thickness or the melt pound or the lead fraction, the break in the ice, are other processes that also act with temperature. So now you have interaction between those, the pound, the snow, the ice thickness, and the leads, and everyone interacts. So we have to understand how these interact one by one, first in a simple way, and then in an interactive way. And that's what the models serve for, not to predict the future, but to tell us how it interacts. Computer, it needs it, it's huge. You know, it's, in 2003, it was like the Earth simulator had 100 teraflop. Now, this time the machine looked like. It's like a big gymnasium, 50 by 60 meter, with 5,000 CPU. But this is nothing with today's computer. is 7 million core, 500,000 teraflop, and 30 kilowatt of 30,000 kilowatt of power consumption. You can imagine. And so these computers are used to do finer and finer grade of the processes I just mentioned. I won't go into the detail of that. I'll give you an example with Mexico, where we went to look at the effect of topography, because it's a basin that accumulates the pollution. So we zoom in by putting all the model characteristic at the finer scale, increasing from the large global scale to finer regional scale to very close to kilometer scale. So at the kilometer scale, we can look at the surface and we can see the sun shining on the mountains. This is just an example, sun shining on the mountain at the morning, at noon, in the evening, or every 10 minutes in the day, or every minute in the day actually can be calculated. So notice this U shape, because I'll show you now the observation. I shift to the observation. Now you can see this L1 or U shape that is Mexico, and you can see the effect of pollution here on this side. On a clear day, it's still polluted. On a polluted day, and it produces cloud. So the pollution, the aerosol, affect the cloud, affect the precipitation, and we can see it from the satellite, and we can simulate it from the model, and we can try to understand how they're linked. It's very, very complex, but we're getting there. We can compare the vertical profile of temperature at different times with observations on many points on the globe, where balloons are launched every point like that on the globe. These serve as a verification. Now I want to draw your attention on this figure. This is the uncertainty on climate due to different processes, carbon dioxide emission, other trace gases. And notice that most of the uncertainty is on cloud and aerosols here. The larger bar, the sum of the two is the largest one. But the biggest of all is the human. So the future of climate depends mostly on us, on human, on what we decide. And this is the unknown part. It's not in the model, it's in our decision making. So in our understanding, the largest uncertainty is currently on cloud and aerosol. That's why we focus so much on it. So if we go to observation and do validation, we have to go through many observation mean, from aircraft to sounding to satellite. I won't go into the details of that, but you can imagine each time an aircraft leaves the airport, it reports on the temperature profile and conditions that we record for the computer to make a better forecast and understanding of the atmosphere. This is our site at 80 degree north at Eureka, Nunavut on Ellesmere Island, where we tested our instruments. It's the far infrared radiometer. And this is a Canadian site where we do really observation of the coldest temperature on Earth. Is -50 in wintertime. And this is where we test our instruments. This instrument has been designed in Quebec with new technology. And it's my team working on this. It's been now accepted to be one of the instruments on board the next mission for the largest mission on cloud and aerosol by NASA. This is another site at Iqaluit that has instruments. And this is a flight we make to test the instrument. You can see the people testing the various conditions in the flight and measuring cloud properties against the reference instruments to make sure that the instrument is performing well. And now what we do is closure experiment. We have to measure all the properties, the radiation, the signature of the clouds, and the actual value of those cloud microphysics together. And we have to make sure that both the measurement, the model simulation, and the in situ measurement of the cloud microphysics is the same. And that's called closure. We have a verification in situ of the result and the model and the measurements. Now we've made, this is one of the constellation we're working on. I'm part of this group, is CloudSat Calypso for measuring cloud and aerosols. And you can see that these instruments are measuring, scanning, measuring various properties of the state of the atmosphere. And I will just give you an example with Calypso here, which is a LiDAR. This is a radar CloudSat. I'll give you an example of what it looks like with CloudSat. So CloudSat is just a strip of 5,000 kilometers where you see clouds appearing. This is water cloud, and you see volcanoes. These are plumes from volcanoes in Kamchatka and in the Aleutian. And we were fortunate to do a campaign during that time to measure the effect. You can see the precipitation in the cloud here straight from the aerosols. This convinced us that the pollution is affecting the precipitation. And this is over thousands of kilometers. This is 1,000 kilometers. The whole thing is 5,000 kilometers. So we've been flying into that region, checking, comparing volcanic and clean air, volcanic being like polluted, could be human, and measuring all the property of the microphysics, ice crystals, and all the properties in details to understand what is the link between ice crystal and pollution and clouds to build better model. Now, the Earth Observing System from NASA is a large suite of instruments that is been working for about 20 years, measuring everything we can think about on Earth's climate. And for instance, here you can see the ocean and the phytoplanktons produced by agriculture, rejection of nitrates, for instance. You can see the blooming you can see the pollution from India produced by aerosol, produced by industrial and human activity. You can see the fire over California due to a burning forest and houses and tragedy there. That has a global signature. You can see the injection of sandstone from the Sahara into the ocean. Actually, the pollution from in Miami is mostly from Saharan dust. That is the main factor for reducing visibility in Miami is the Saharan dust on the other side of the ocean. We have volcanoes.
Jean-Pierre, excuse me, Jean-Pierre. I'm sorry to interrupt. It's fascinating, but I'm just wondering how you manage the thing with Patrick.
I'm almost finished.
Yeah, because I was said that it was 30 minutes each, or you're a little further than 30 minutes.
Let me finish my conclusion. And
of course. I didn't.
I have 2 more slides.
I just wanted to make sure that Patrick is okay with that. Okay, go ahead, Jean-Pierre.
Thank you so much. So the next big mission is a $2 billion mission. It's going to be measuring like never before at high resolution on the whole globe, cloud feedback, aerosol interaction with many instruments. Unfortunately, we're the only non-American instrument from UQAM on this mission, and it's indispensable. It's a necessary instrument called the Far Infrared Radiometer, TICFIRE, and we're working hard on it. And the Space Agency is backing us up on this. So we're going to be measuring over a very wide range of at high resolution of wavelength from microwave to UV at 500 meters to 2 kilometers resolution scale. So in summary, the climate is modeled as a budget of stocks and flow. I wanted to convince that it's controlled by nonlinear feedback processes that are complex, and each scientist has one aspect of it. We have to put them together to figure out the result. And the dynamic climate system is modeled by a set of budget equations, conservative variable. Each processes must be carefully designed to represent nature. And that's the artistic part. We'll try to do the best. So that's where it varies from people to people. That's our understanding. And climate simulation needs large computer resource and huge data set. Now, observation and validation are central for reducing the uncertainty, because that's where we verify our understanding. Large ground-based observation, airborne campaign, satellite are essential to close the loop on the climate response. And what I would like you to remember is that models are primarily for building our knowledge, not predicting the future that depends only on us. That's the largest uncertainty bar. Model won't predict the future. It's us that decide what we do. Thank you. So I pass the floor to...
Thank you so much, Jean-Pierre.